Swayam Prabha. Digital India. Educated India.
In this course, we'll be dealing with classical controls for the linear systems. Also, we have to assume the system is time invariant. To prove the linearity of the system, we have to follow the principle of superposition, under which there are two important laws. One is the law of additivity, another is the law of homogeneity. And once the system follows both the rules, then we can say the system is linear. And also we have to satisfy the system time invariant or not. Once the system is time invariant and linear, then we can say system is linear time invariant system. We'll have some example to validate these properties, then we'll conclude the lecture. As you know, all physical systems are non-linear in nature. But to design control algorithm, in this course, we need to consider the linear system. This is my linear system, y equal to fx. But how will validate the system what you have is linear or not? This answer can be given by the rule which is called principle of superposition. So now I'm going to validate this system is linear or not. And through principle of superposition, we can validate principle of superposition. Under these two conditions we have to test. First is additivity test, and second is homogeneity test. Let me discuss what is additivity test. So let's assume, let me write additivity test. Let's consider we have system here. System what you have from the physical system or nonlinear system, y equal to fx, and I'm applying to this system to different input. Let me say this is plus. I'm applying to the summing point x1 and another x2, and the output from this block we can say x1 plus x2, and the response from this block we can say y equal to, or I can say y equal to y dash, I can write f of x1 plus x2. And if you notice in this loop, we are actually adding the state or inputs, and we are applying this summed input to the function. But instead of this, if you apply x1 to the system y equal to fx, and x2 if we apply to the same system y equal to fx, and the output from this block we can write fx1, and from this block we can write fx2. And if you sum both the output to the summing point, we have output from the summing point f of x1 plus f of x2. Now, if y, let me write this y double dash. If y dash equal to y double dash, we can say the system follow the additivity rule. And we need to go to the second test, which is the homogeneity test. In homogeneity, let's consider the same system y equal to fx. This is my system. And let's apply input, which is x of t. And the output we can write. And if you scale this output, some scaling factor k, and we can get a into y. This is, let me assume this is y of t, for example. The same output, same input you are applying xt, which is going to the function f of x, and we are getting the output yt. And if you multiply this yt by scaling factor k, we have the output k yt. I can write. If you notice here, we are multiplying the scaling factor k to the output y of t after the system response. Now, instead of this, if we multiply this scaling factor before we apply to the system, suppose this is my k, and the output from this after multiplication, I can write k xt. And this, if we apply to the system, which is basically y equal to fx, and the output from this system we can write y dash. Let me write y dash, and this is, it is y double dash, and I let write y dash. If y dash equal to y double dash, I can say the system follow the homogeneity rule. If it does not follow, then does not satisfy homogeneity test. Does not satisfy the homogeneity. If the system what you are getting from physical system follow both additivity and homogeneity, we can say that the system is linear. Let's take an example which can validate the above theory. So y equal to fx, and the fx function is x squared divided by 16. We'll check the system is linear or not. So we'll go two tests. One is the homogeneity test, another is the additivity test. Solution. First, let's go with the additivity test. Additivity test. We'll go the same steps what we have done. We have summing point, and we apply two inputs. for the system x1 and another input x2, and we'll sum the inputs, and the output from this block we can write x1 plus x2. And this response will apply to the system y equal to fx, which is x square plus divided by 16. And the output from this block we can write if x1 plus x2 equal to x1 plus x2 squared divided by 16. And in the another case, we'll apply the system individually to the system. So we have system f of x. This is basically y equal to fx. I can write the same system y equal to fx, and we'll apply here x1 for this system, x2, and the output from this we can write fx1 from this block fx2, and if you sum both the output through the summing point, we can write f of x1 plus f of x2, and we can write x1 squared divided by 16 plus x2 squared divided by 16. So if you notice, the response from this block and this block are different. So the system y equal to fx does not satisfy the additivity test. With this condition also, we can say system is not linear, but still we can test the homogeneity test as well. Let's go to the homogeneity test. To be system linear, we have to test both homogeneity test and additivity test. If both the conditions satisfy, then we can say system is linear. But in this case, through additivity test, system already is not linear. But still you can say homogeneity test. In homogeneity test, what we'll do is this is let's assume this is the x of t is some reference input, and I am scaling this input by a scaling factor a, and the output from this summing point I can write ax, and if we apply this ax response to the system fx, we can come up with the output y equal to f ax, or we can write ax squared divided by 16, which is a squared x squared divided by 16. Now, if you notice here, we are multiplying the reference input xt by the scaling factor a before we apply to the system, basically pre-multiplication. Now, if we apply x of t as it is to the system f of x, and the output from this block we can write x square by 16. And if you now multiply this output with a scaling factor a, and the output from this multiplication block, we can come up with ax square divided by 16. Now, if you notice, the output from this line and this line are different. So, but basically this function and this function are different, the output from these blocks. So we can say, hence, the system does not satisfy the homogeneity, hence the system is not linear. So both the conditions not satisfied. I mean, the system does not follow both the homogeneity test and additivity test. So hence the system is not linear. So now we can test whether the system is linear or not. But there are another condition also need to be satisfied before you design control synthesis. So to the above test, we can say the system is linear or not. Now, the system which comes out to be linear, this system also needs to be time invariant. So once the system is linear time invariant, or LTI, we can easily design the control. Because in this course, we'll be designing the control algorithm for LTI system. So through the above theorem, we can check my system is linear or not. Now also you have to check the system also time varying or invariant. That is also needed to prove. So let's go how we can prove the system is time invariant or not. So let me define definition of time invariant or variant. Any delay applied in the input must be reflected in the output. So how it is can be defined? Let's go to the blocks, and it will be easy to understand. So we have system. We'll check the system is time varying or not. System, and we are applying some reference input, which is x of t, for example, and we are getting some output from the system. Let me write, this is my y of t is my output from the system. Now, if you apply a delay to this output, delay, let me write t naught, some delay t naught to this output, we can write the output by y t minus t naught. Now, instead of applying a delay to the output, if you apply a delay to the input function, which is x of t, delay by T naught. So we can come up with the output like xt minus T naught. And if we apply this xt minus T naught to my system, and we can write this is y dash t. So now if y t minus T naught equal to y dash t, then I can say system is time invariant. If it is not satisfied, then we can say system time varying. So this is how we can check the system is time varying or not. Here basically most of the system where the coefficients are constant, assumed to be constant, basically those kind of system are basically time invariant system. Now let's take an example that I think probably will be clear. Example, y of t equal to tx of t. Let's check whether the system LTI or not. So here also we'll check the linearity, whether the system is linear or not. Also the system is time invariant or not. So let's go step by step. Let's assume the inputs are given inputs. I'm not writing the block in blocks, just it is same way you can write it mathematically. Given inputs are x1 t and x2 t. Now for the x1 of t, the output I'm getting through the system txt, tx1 t, or I can write y1 t. And for the input x2 t, I'm writing tx2 t and output y2 t. We can write y1 t plus y2 t equal to t x1 of t plus t x2 of t. Now, if we scale the inputs by a and b, which else we can write ax1 plus bx2, we can write t ax1 plus bx2 equal to atx1 plus btx2. And from this also you can write a1 y1 t plus b y2 t. So from this I can say the system follows. Hence you can check through blocks. It will be also easy to understand. I'm not doing it. So hence the system follows both additivity and homogeneity. The system is linear. Now we'll go to the test of system is linear or not. Sorry, linear system is time varying or not. So for this, what we'll do is, if we checking time invariant or not. So here, if the input x of t is delayed by t naught, and also if we apply the same to the output, and if we apply to the system, we have x t minus t naught. From this we can write tx t minus t naught or y dash t, and y t minus t naught. From this I can write t minus t naught x t minus t naught. So if you notice here, you can check this through the blocks, what I've done in the testing of system time invariant or not. You can check in this block. So this is the exactly same expression you'll be getting. So now from this, it is clear that both the output are not equal. Both are not equal. Hence, the system is not time invariant. This is how we can check the system is time varying or not. Let's take another example. Example 2. We have system y of t x square t. And let's check whether system is, let's check whether the system is LTI or not. Let's go step by step. Solution. First, we'll check the system is linear or not. So for this, we'll first test the additivity test. Then we'll move to the LTI homogeneity test. So through additivity test, if you consider there's two inputs, x1 and x2, we can write from x1 plus x2, we can write x1 plus, this is my system, through system we can write x1 x2 square equal to x1 square plus x2 square plus 2 x1 x2, and y1 plus y2 x1 plus x2 square, and let me write this y dash, and this is y double dash, this is y dash. So through blocks also you'll get the same kind of response. So we can check y dash not equal to y double dash. So does not follow the additivity property. Let's say the homogeneity property. So we have homogeneity. We have input x of t we are applying to the system, and we are getting output which is scaled by k, scaled by k, and we are having k x squared t, or I can write y dash t. And similarly, x of t will scale first by scaled by k, and we are getting k x of t, and we apply this kxt to the system, and we'll get k square x square t double dash t. So from this I can write y dash t equal to y double dash t, not equal to this. The system does not follow the homogeneity properties. Hence the system is not linear. So system does not follow both the additivity and homogeneity. So hence the system is not linear. So now we'll go to the next part, whether the system is time varying or not. So we'll test through the blocks. We have x of t is a reference input, and I am applying to the system, and we are getting the output x squared t and delay by t naught, and we are getting x squared t minus t naught, or I can write y t minus t naught. Okay, and now we'll apply the delay to the system input x of t, then we'll apply to the system. First we'll apply delay here by t naught, and we apply this delayed input to the system. This is my xt minus t naught. This is system, and we are getting the output x square t minus t naught, which is some y dash. So if you notice, y t minus t naught same as y dash. The system is time invariant. It is good that the system follows the time invariant properties, but the system does not follow the linearity property. So I can't say, so the system is not linear, but time invariant. So this is how we can check the system is LTI or not, system is time invariant or not, system is linear or not. So this is how we'll be doing. So now in the next lecture, we'll be talking why we have to consider LTI system for designing control. That is the very important part we'll be talking. So let's stop it here. We'll be continuing from the next lecture. Thank you.